All right, everybody. Hopefully you're all here for OpenEdge database performance, concurrency, or another, the subtitle, how we pretend to get lots of stuff done all at once. Because as we know, computers really only do one thing at a time. I am Tom Bascom. I'm with White Star Software. We are the world's oldest independent consulting organization, which is devoted entirely to OpenEdge. Progress OpenEdge. We've been doing this since 1987, which coincidentally was the same time I started working with Progress. We work with all sorts of different customers, from very large to very small, working with very structured, highly organized environments or very chaotic environments. We've seen it all. And we love to come out and share our experiences with the community, so here we are. Okay, so what we're going to talk about here today, we're going to talk about record locks and transactions, because that's a fairly important part of concurrency within your application. And then we're going to talk about what a latch is and why that's an important feature of the OpenEdge database. And then some of the dangers of virtualization and what the impact of Pneuma architectures is. So these are kind of the things we're going to cover in this little chat. So first we'll talk about record locks and transactions. OpenEdge sessions, as you might know, are single-threaded. So the 4GL doesn't support any kind of multi-threaded capabilities at all. Anything you do, if you get a record lock or you're blocked waiting for a record, you have to wait. You can't just spawn off another thread and go and do something else. So if a session gets blocked, it can block multiple users. So you can have one person out there, Paul can be out there holding onto a control record with an exclusive lock, and if everybody else in the room needs that record, they're going to have to wait for him. And so that obviously has a big impact on concurrency, and it makes it important that you write your code in an effective and efficient way so that you can tightly scope your code to minimize the potential for those lock conflicts. And paying attention to that kind of thing is pretty critical. You want to especially avoid accidental downgrades to share lock, because the default Progress lock is a share lock. So when you go from an exclusive lock and you go out of scope, it becomes a share lock by default if you haven't carefully scoped your transaction correctly. And you should always explicitly specify a type of a lock. Record locks and transactions are pretty closely related to one another. So when you look at a transaction or a buffer scope or a lock scope, you really have to think about all those things all together. Now, the last time we were all together for real, I did a presentation on this topic. It was on scope, which you can download from the Pug Challenge website from 2019. It's about an hour-long presentation that goes into all the details of coding around making sure that your scope is the way that you want it to be. But the best practice, it all boils down to, is to use a strong scoped buffer and to keep it very, very small. So you do something like do for UPD customer transaction, you find it with an exclusive lock, given a particular name, and then you make your change and you end. And that way your transaction, your record, and your lock are all very tightly coupled together. They don't expand out beyond where you expect them to be, and you're not leaking locks into the rest of the application and blocking other users. That's really important. But if you need more detail on that, download that presentation, take a look at that, and get some more info there. So beyond that, what we worry about is the latch mechanism within the database. The database server itself maintains concurrency through the use of something called a latch, which is how access to shared memory is controlled in such a way that lots of people can access shared memory very, very quickly in a highly concurrent manner without blocking each other. So what is a latch anyway? Well, one aspect of a latch is that it's the ultimate database performance bottleneck. Once you've eliminated I/O, once you've eliminated everything else that's in your way, the latches are what's going to hold you back. So if you do a really good job taking care of your I/O problems and you've done a really good job getting your code optimized, latches are your last performance bottleneck. More technically, it's a lock on shared memory. If you think back to your college days, so you might have studied this a little bit, it's something called a mutex, or mutual exclusion lock, or a spin lock. That's another name for it. There are a lot of different names for them. They must be implemented as an atomic operation. It's really, really important that the operating system side of things is not interruptible when you're taking a latch. So you can't have two instructions. It has to be a single machine instruction that locks the latch. And at the machine code level, this is frequently either a test and set or a compare and swap instruction. So it's an instruction that does two things at once. There are a couple of different ways that this can be done, but those are the two usual suspects. And why are they important? Well, they coordinate the access to shared memory. And shared memory is critical to effective use of the operating system. And a spin lock is much more performant than an alternate method of locking shared memory, like using a semaphore. Because when you use a semaphore, you're basically going to sleep. And it's much faster to just execute a few instructions and keep trying than it is to go to sleep, wake up, go to sleep, wake up. Instead, just spin. Go faster, faster, faster. Kind of like some people drive around in the parking lot. Have you ever noticed that? They're looking for space and they're just going faster and faster. Anyway, because latches are shared, though, they can be a source of contention. So if you have lots of users that are all trying to acquire a latch at once, then there's a lot of CPU utilization involved in that, and that can obviously drive a lot of load on your server. Or if a user is killed while they're holding a latch, that's why the database will sometimes crash as a result, because the database doesn't have enough information to back out of that situation, and so it says, well, I'm sorry, but I have to stop. It's not really protecting you from corruption. It's just saying, I don't know how to undo this, and I can't get out of this situation, so I'm going to shut down. Now, you may think you're just doing a fine no lock. So you're finding a lot of data, you're not getting any locks. What do you need a latch for, right? Anybody ever have that question? Ever think about that once in a while? When you access data, though, whether you need that data to read it or write it, you're accessing shared memory. And Progress needs to keep track of that access to shared memory for some fairly important reasons. One of the optimizations that Progress uses in order to keep the database fast is to keep track of how frequently things are used in memory, so that when it needs to swap something out of memory, it doesn't swap out the new stuff, but swaps out the old stuff that you're not using. That's called the least recently used algorithm. And we'll talk about that in just a moment. And even if you have a client server session, you're still using shared memory, because that remote server is accessing the shared memory on your behalf. So even though you're on a remote PC, the connection that you're coming into has a server which is then accessing the database for you. So there's really no way around it. So some of the drivers, dirty reads, no lock reads, because they skip all the other things, can still drive some concurrency, Rapid readers. So a rapid reader will strain the database by very, very rapidly reading records over and over and over again. Often this is a small number of processes which are doing a large amount of I/O. So you might have 2 or 3 people that are running reports, that are doing table scans, all swimming through your database. They're swimming through a lot of different blocks, but they're doing a lot of it. So there's a lot of activity involved in that. The opposite of that is something called a hotspot. So you might have many processes that are focused on just a single piece of data. So you got everybody hammering on this one spot instead of just a couple of people hammering on a lot of spots. So it's kind of the flip side of the coin. And one of the more significant sources of latch contention is the LRU chain, the least recently used chain. So the DB engine uses this to decide which block to replace when it needs to read a new one from disk. So as you fill up the buffer pool, you're doing that so that you don't have to do I/O. Once the buffer pool is full, when you need a new block, it has to decide, well, which of these blocks that I already have do I push out of the way to bring in the new one? You don't want to push a fresh block out of the way because you're probably going to read that block again. That's something called locality of reference. So you want to take a block that hasn't been accessed for a long time and push that out to disk. That's how the LRU chain works. And whenever any block is referenced, it has to be moved from the wherever it is to the head of the chain. That's how we keep them least recently used. And that includes whether you're doing a no-lock find or whether you're doing things with or without locks, because it's just a reference to memory. And basically that results in unused blocks gradually moving down to the least recently used head of the side of the chain, while the frequently used blocks move to the most recently used side of the chain. So it kind of keeps things segregated that way. And this can become a bottleneck because every time you touch a block, we have to move that block from here over to there, which means that you have to update half a dozen pointers. And that all has to be done atomically. You have to do all those updates within a single thread of execution. If somebody interrupts that, so you've broken this block out, you're starting to move it over there, but you haven't put it on the head of the chain yet. If somebody else gets the processor and starts working with this block, now you have a corrupt LRU chain because two different things have been broken. They're both going to get written to the head. One of them's going to get lost, and that's not going to work. So that's why latching is critical to this whole process. And that's where you go through the thing here. So to safely update it, it has to be locked. And because many people need to do it, the latch can form a bottleneck. So ultimately, that's a single thread of execution through the database. There's only one thread of that kind of operation that can occur. And all the different latches in the database are of a similar nature. They all have a single thread that's allowed to update them. Luckily, there are many different latches, so you can spread that work around, but in any individual latch, there's only one. So what's the spin have to do with it? Well, the high performance is obtained by testing the latch continuously. So remember I told you earlier that it's a test and set instruction? Well, what actually happens is it's a test, 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 test. Oh, it looks like I might be able to get it, test and set. That makes it a little bit more efficient because you don't have to go out across the caches between the various cores and keep them coordinated. And you limit the resource consumption there by the spin algorithm by saying, I'm going to spin this many times. So by default, that's 3,000 times the number of, 6,000 times the number of cores. You probably don't want to really use that. That's a very large number on modern machines. But 10,000, 20,000, something like that. After you get to the spin value, the process will take a nap. It'll say, okay, I've been trying long enough, time for me to take a nap. And it'll take a nap from the initial nap value, which defaults to 10 milliseconds, all the way up to whatever nap max is, which these days is usually 500 milliseconds. It used to be 2,000, which is a long time. That's a 2-second nap. The more times it fails to get the lock, the longer the nap will be. And then there are some additional optimizations that you can get into deep within the engine. As I mentioned, only one process can hold a specific latch at a time. So ultimately that leads to these bottlenecks called latch contention bottlenecks, where you have people that are waiting on that latch, and then you have to figure out, well, how do we get around that? You can not process more than one latch, you cannot process more latch requests for any one latch than a single CPU core can handle, but there are a lot of different latches, and different threads can simultaneously compete for different latches. So then you might be after the LRU latch, Paul might be after the OM latch, Peter might be after the MTX latch. All those things can go on simultaneously, but there's only one thread for each of them. So if you have a latch contention issue, what do you do about it? Well, there are three things that you can do. You can request fewer latches, you can spread your locking over more latches, or you can get faster cores. How do you do those things? Well, getting faster cores is easy. You just call up your supplier and you order a new one, and if the chips are available, you're all set. So, requesting fewer latches. Well, there's a couple of different ways that you can request fewer latches. One, if you have 10.2b08 or later, you can use a parameter called LRU skips. Because in 10.2b, in anything where you're not using LRU skips, the most likely latch contention you have is the LRU chain. LRU skips basically says, instead of updating the LRU chain every time I touch every block, only update it every n times I check that block. So what that'll do is it'll make it so that the blocks migrate in one direction or the other more slowly. And the block that gets flushed won't be the strictly least recently used block. It'll be a block that is kind of hasn't been used very often, which is good enough, actually. So what we usually suggest is that you set LRU skips to 100. That basically means that you're only checking the LRU chain about 1% as frequently as you used to. And that will make your LRU contention essentially vanish. There's a feature which results in fewer latch requests called optimistic cursors in version 12. And this reduces the need for latching certain reads of index blocks. So basically, the database assumes that you're looking at the correct block and doesn't latch there unless there's an actual mistake. So it says, I'm going to be optimistic about this. I'm going to assume that you actually know what you're doing and go from there. Another option is to fix your code, because a lot of times this kind of activity is being driven by code that is not terribly efficient. This gets into some of the discussion we had earlier in the day about code that reads control tables very, very frequently and over and over and over, or code that is doing table scans that it doesn't need to do, things like that. So sometimes there are things you can do in your code to request fewer latches and therefore have less latch contention to deal with. Can't always do that, but sometimes you can find some opportunities there. Getting more latches is another option, and one of the ways that you get more latches is to upgrade. Upgrades are effective because over time the database engine crew has done a lot of work to improve the algorithms behind these things. They've added more latches to the database. So in cases where there's a limited number of latches for a certain purpose, they may have expanded that number. The hash latch factor parameter here is a good example of that, where the number of BHT latches has become a problem now that LRU skips is making the LRU latch no longer the primary bottleneck. And so this basically gives you more BHT latches to use as you go forward with progress. There used to be 1,024, I think, and then the default with 11.7 changed to 10% of whatever the dash hash value is, which is 25% of the big B value. So what's that work out to? 2.5% of whatever you set big B to, which is probably a lot more than 1024. Or you can use more blocks. So a possibility is that you're having an uneven balance between the BF 1, 2, 3, and 4 latches, which are really just an accounting fiction because every block has an individual latch, but it would be very difficult to report that. So Progress reports on 4 buckets of latches called BF1, BF2, BF3, BF4. And typically you're going to see the same amount of activity on all 4 of those counters. But sometimes you see one of those counters is much higher than one of the others. And that's usually indicative that you have one block somewhere, the somewhere is a little difficult, that is the subject of the hotspot that I talked about a couple of slides ago, where everybody is accessing that one block. If you can figure out what that block is, then you take that block and you say, I don't think I want that to be in a 128 rows per block area. I'm going to put it in a one block area, and I'm going to spread those 12 records over 12 blocks instead of having them all in one. And that kind of spreads things out a little bit. You can sometimes find that table by looking at the ratio between reads of the table and the size of the table. So if you're reading it a million times more often than its size, you know that that's probably a hotspot type of block. It really only works for very small tables, and it doesn't do anything about the indexes, but it does help if you have data contention for those sorts of blocks. And lastly, faster cores. So since your bottleneck is really how fast a core can actually get the work done, getting a faster core will help you out with that. What won't help you out is more cores. Because remember, the whole problem here is the single-threaded access of a core to your data. Having more cores just means that more people are trying harder, which means it's like a traffic jam. It's going to be an even worse traffic jam. Adding more drivers doesn't solve traffic problems. Adding faster cars solves traffic problems. Although, well, that's kind of, anybody here ever drive with Mike? If everybody drove like Mike, traffic would move a lot faster. Anyway, so there's a trade-off between the number of cores per socket and the CPU speed. If you go to Intel's website and you look at their comparison screens between the various cores that they have to offer and the processors and the packages, you'll note that there's a very interesting relationship between number of cores and clock speed of those cores. The faster the clock speed, the fewer cores per chip. So if you want to go fast, you want the smaller packages. You want the 8-core and the 6-core packages, not the 12-core and the 24-core and the 48-core packages, because they're all slower. And sometimes it's cheaper to get a fewer number of cores that go faster than to get lots and lots of cores that go slow. So it's another one of those things, kind of like SSD disks, where you actually have that ability to spend less money to get better performance. That's always fun. You should always do that. So within the OpenEdge environment, there are some important latches. Some of the ones that you'll see most frequently are these here. LRU, we already talked about. MTX, that's a microtransaction. That's when you're committing data to disk. BHT is the buffer hash table. So this is when we're looking up a block so that we can figure out which block it is we need to update. OM is the object manager. So every time you reference a table or an index or something like that, it has to be looked up. BF latches we talked about a little earlier. SEQs are your sequence updates. LHT is the lock hash table. So when you're locking records, this comes into play. LKF is the lock table free list. So as locks are being freed, they're moving on and off of there. And the lock purge table will sometimes show up, especially, I think it was 10.2 something or other. There was a problem with LKP all of a sudden went crazy because something happened in the database engine. You don't see that one so much today. So what do you do if you have a latch contention problem? If you have a lot of naps on LRU, then the obvious thing to do is to set LRU skips to 100. If you have a really big system with a lot of users and a lot of activity, then a value more than 100 might be a very sensible thing to do, but most people, most of the time, are going to be pretty happy with LRU skips 100. As I mentioned earlier, the order of the LRU chain is no longer perfect, but it's still pretty good. You know, you've got stuff that hasn't been used very much, and you've got stuff that's used frequently. And that's really the separation that you need to make. You get quickly diminishing returns with very large values. It doesn't make a whole lot of sense to set LRU skips to 10,000 or 1,000,000 or something like that. That's really not going to get you where you want to go. Setting it to 100, maybe 200, 500, those are not crazy values. Setting it to 1,000, you're starting to get into crazy land. What you especially don't want is a very small buffer pool, -B, and a very large LRU skips. If you think about it, that's not going to work out very well. If you have, you know, if you've only got 1,000 blocks and you're only counting them once every 1,000 times you touch them, they're not going to be in the order that you're looking for. So don't do that. How about if you have MTX naps? Well, MTX naps occur when you're committing data to disk. So really, you're most frequently going to see this when you're working with a SAN and you have a slow I/O subsystem that doesn't really do writes very quickly. And really about the only way you can fix that is to get faster disks. Stop using SANs, for instance. That's always a good idea. There's no such thing as a high-performance SAN. Those things don't exist. SANs are not there to make your database go faster. They're there to make your storage administrator's life easier.
Sorry, there's a question from the chat. Gareth is asking, what is the recommendation if you are running multiple PAS-OE instances connecting via shared memory? Are more cores not better in this case due to multi-threading?
No. Well, not for database performance, they're not. If you got to look at what your performance is. If the performance of your PAS processes that are connecting via shared memory is being dominated by executing 4GL, then maybe more cores would be helpful, but it's not going to help your database performance. So the other thing you can do is review your code for MTX here, and if possible, then reduce the rate at which you commit transactions. Maybe you have transaction scoping problems like we talked about earlier, or maybe you're doing lots of very small transactions that could be grouped into a larger set of transactions and therefore do fewer write operations. So group them all together like Patrice was showing last night. If you have BHT naps, then you have managed to get past the LRU bottleneck, so that's good. You're already in a good place, but you're now on the next bottleneck. And that means that you almost certainly have some very, very high read rates. So the first thing you should do is start looking at, why do I have these very, very high read rates? Is my read activity sensible for my application? Is there something going on here that I can address from a coding perspective? If you can't, then your best bet is going to be faster cores. Other than that, you've got hash latch factor and optimistic cursors that might help you as you go forward in later OpenEdge releases. The OM latch, so you want to make sure that you have OM size set to be equal to the number of objects, tables, indexes, and lobs that you have in your database. So make sure that OM size, the startup parameter, is set to at least the result of the count of your storage objects. It defaults to 1024, which is great for the sports database. It's not necessarily so good for real databases. Real databases probably need a larger value. We talked a little bit about BF1234. Like I said, they're an accounting fiction. There's basically 4 buckets, so think of it as modulo 4 of whatever the block number is. And the chances are pretty good, if you've got some contention on this, that it is because you have that highly active small table. And the easy way to find that is to look for the tables that are being read at a high ratio to the size of the table. There's probably something that's going to stand out like a sore thumb, and it's really not going to be too difficult to find. But another possibility is you might see that resource 96 or 192 is waiting on a BKSH. You can see this in ProMon, or you can see it in ProTop. And if that's happening, then what you're looking at is activity on the sequence block, because those are the 2 sequence blocks, depending on whether you have an 8K or a 4K database. So another thing that you might have is you might have lots of just kind of general napping rather than a specific problem with a specific latch. And if you do, the way you see that is that you see that there are a lot of latch weights, which you'll see in ProTop or ProMon or whatever you're using to monitor your database. You may see a relatively high percentage of system CPU utilization. There will be spare capacity from a user perspective, the user percentage of CPU utilization. And what you can do when that's happening to get better performance is to increase the value of dash spin. So this is a case where maybe you started out with 10,000, you've got 50% of your CPU available, but you're napping a lot. So increase spin, go up to 50,000, and you'll spin longer, you'll use more CPU, but your throughput of your database may improve. The inverse of that is CPU exhaustion. So in this case, you look at it and you're using most of your CPU. You're in the high 90s, 95, 98% CPU utilization. And the number of latch requests has gone down. Nobody's napping, but the users are complaining that the system's not very responsive, which makes sense because you're using a lot of CPU. And basically what's happening here is the spins can't complete before your process gets rescheduled by the operating system. So you've used more CPU power than you have available. That means you set spin too high. So reduce the value of dash spin. This might be a case where you've allowed the defaults to occur and you have a server that maybe you bought one of those servers with 48 cores and you enabled hyperthreading, so you've got 96 of them. And so 96 times 6,000 is dash spin of, what's that work out to? 6 million, something like that? I don't know, something crazy. So in that kind of a case, you might very well want to reduce dash spin down to something a lot more reasonable. So suggested value. Be very careful if you see a knowledge base article or something like that that says, hey, set it to the number of CPUs times X. There's lots of articles like that. The knowledge base is full of them. Basically, this is a very old recommendation, and you really don't need to be following it. It's easy to find them, but there is a knowledge base that is more reliable, this one here, that tells you how to not do it that way. And basically go back to what I was saying earlier. Okay, so is there one spin to rule them all? No. We suggest that most people will be okay with 10 to 20,000, something along those lines. We have some customers who are happy at 100,000 or higher. We have at least one customer who's using 1 million, but that's a very, very special case. We have another customer who has had to drop it to 5,000, and actually recently they've had to go even lower than that because they have overcommitted that particular server. And they're having some issues with what's called Pneuma. And basically you have to monitor your application and decide whether to tune it up or down based on some of the criteria we talked about earlier. If increasing spin consistently increases throughput, then go up. If decreasing it works, then go down. Watch out for those Pneuma boundaries. I guess I got to hurry up a bit. Okay.
The block was until 6, I'm afraid.
Okay, well, we've just got a couple of short things to talk about here. So there are some dangers with virtualization. Virtualization is a great technology for certain things. There are classes of problems that virtualization is great for. One of the things it's not great for is making a database server go faster. If you're virtualizing because you're expecting your database server to be really happy that you have done that, you're making a mistake. Co-scheduling is a problem in a virtualization environment. It's basically the situation where more is not better. When your VM is ready to run, it needs to have, hey guys, when your VM is ready to run, it needs to have the resources that it needs to have in order to be able to run. So if you need to have 14 virtual cores in order to run your VM on a server that has 16, but somebody else only needs 3, guess who's going to get to run? The guy with only 3. So you want to right-size your environment to be able to fit in there. Oversizing your VM is really going to make things better. So this isn't a case where you want to just go bigger, bigger, bigger all the time. You want to have things the size they need to be and not any larger. And always leave a little extra capacity in the virtualization environment so that you are able to run all of your workload at the same time. You're not trying to trade off various servers that are not important here. You have a critical, mission-critical application that you're running. The other issue is Pneuma. And Pneuma is a problem because Pneuma stands for non-uniform memory allocation. And latches are frequently accessed memory locations. So if your memory is not uniform, that means that some of it is going to be favored over other. So you don't want to have a situation where some memory is faster than other memory, because that's going to slow you down. And the CPU caches have to coordinate all of that. So the more you're spreading that over, the harder you're making the job on the processors. Coordinating those caches across the bus is really complex and expensive. Testing a value is relatively cheap because you can do that test and it doesn't really require any updates of the local caches. But if you update it, set it to a new value, then you have to invalidate all the other caches, and that is very expensive. So it's a lot more expensive if those are on different chips. So if you're all within one chip and you've got 3 or 4 or 6 cores in that chip, that's a very short distance. It doesn't take very long to do that. But if you get a chip here and a chip here, instead of going like this, you're going over here, back. That takes a lot longer. And then it's even worse if you have multiple boards. So you're going not just from a chip to another chip, but then you're going out on the board and up and into another chip. The more distance you have to cover, the longer all that's going to take, because you're limited by the speed of light. So that's why Pneuma is a problem with too many cores. You want your cores physically close to each other. Ideally, you want them all within a single chip. If they can't be on the same chip, you definitely want them on the same board. You don't want a situation where your virtualization environment has chosen to spread them broadly, as widely as possible. You want affinity to keep them as close as they possibly can, so that the signals don't have to go very far. So anyway, that's how that all works. You can mitigate some of the impact of Pneuma by keeping the CPU and the memory utilization low. So if you know you're on a Pneuma server and there's nothing you can do about it, one of the things you can do is just kind of try not to let your CPU go too high. You do that by not setting spin too high. So we were talking earlier about that customer who's had to lower their dash spin value. That's because if they set it any higher, they cross that Pneuma boundary. And when they cross that Pneuma boundary, it's like falling off the table. Performance really goes in the tank at that point. Likewise, setting your memory too high can also be a problem, because that means now you're accessing memory that is associated with a different chip, and that's your farm memory. So making an access to that memory is more expensive than the memory which is mapped to the chips that you're ordinarily using. So you want to keep the CPU count and the RAM allocation beneath those Pneuma boundaries as much as possible. You want to try to get your virtualization manager, whatever your hypervisor is, to help you out with that. By default, some virtualization wants to spread things as wide as possible. That's not what you want. You want to keep it tightly packed. I think that's gotten a lot better in recent years, but early on in the virtualization game, the trick was they were trying to spread things out. Now you have more options to keep things together. Or buy fewer, faster cores and avoid Pneuma in the first place. That's your other hoped for option. And try to avoid the temptation of throwing too many cores at your problem, because what will happen is you'll have bought all these cores, they won't be doing anything, and your users will be complaining that your system is slow. Adding cores is only going to make it slower. Okay, questions? Chat? Yes.
Suppose you have a server that is going to cross a Pneuma boundary. Is there a way within the process list of the server to kind of assign affinity to a database server and its servers and its APWs kind of to one Pneuma node, and then the other database on the other Pneuma node?
Okay. So you're asking, can you use operating system tools to assign processes to particular cores? And memory. Yes, you can, but it's a lot harder than it sounds. And if you've got multiple databases, you probably have clients that are connecting to multiple databases, and it's all going to fall apart at that point. So one of the things you can do, though, is instead of taking that approach, partition it further. So break it up into two virtual machines, one for each database, and use client-server connections to connect to those databases that are now in smaller, more tightly controlled partitions. Now, that assumes that you've done all the work to make your application efficient from a client-server perspective, which is a challenge, but if you have an application which does well in a client-server environment, that can be a big help. Other questions?
I'm asking here on the chat.
Yes, sir.
You talked about the number of cores for your database access.
Yes.
When you're using an app server, it normally sits on the same machine.
Yes.
Is that also the 8 boundary that you use, or you said, okay, for cases when you have an app server and a database server on the same machine, you do something different?
So the question is, if you have app servers, do I still recommend that you try to stay within an 8 core or less kind of a boundary? Yes, I would still try to do that. But again, like Gareth's question earlier, it's going to depend a little bit on how much of the workload that is coming out of those app servers is just generic 4GL processing versus database access. If you have a lot of 4GL processing and not so much database access, then you might get away with a little bit more. It's also something where you might want to reconsider whether the app servers should be connecting via shared memory or should be in another LPAR and connecting client server. And if you listen to Progress talk about things like PAS-OE and implementing it in Docker containers and those kinds of scenarios, those are all going to be client-server connections. So we all have to start figuring out how to be efficient at connecting client-server and putting together good architectures that way. And Progress probably needs to pay a lot of attention to that as well, and I know they are paying a lot of attention to that kind of stuff. You've got a lot of new features, server-side joins, and all the prefetch stuff that they've done recently are all intended to help to improve that performance profile right there, because that is the future. We're all heading that way, whether we like it or not. So that's my answer to that. All right. Other questions? Yes.
How close can you reach this performance that you get on shared memory by for remote connections when you tune?
How close can you get it? So the question is, how close can you get client-server performance to shared memory performance? And that really depends a lot on the application. If your application is intensely using find statements, individual find statements, you're going to see a much bigger painful performance problem there. If you use a lot of queries, for each no-lock queries, then you can get the performance very, very close. And in fact, you can get a for each no-lock query oriented test case to run faster client-server than you can shared memory, because you actually have two processors working in parallel in that one scenario. Now, most applications, that's not really your workload. You have some workload that's like that, and you have some workload that is find statements. So there's a mix. But if to the degree that you have things that are more query-like, you can get extremely good performance client-server. But legacy applications in particular, that's a real challenge. Other questions? Paul, anything on the chat? Okay, well, thank you very much.